Francesca.
Okay, I don't see if it is a recording or not. Is it okay?
It is recording, yes.
Okay, so hello everyone. I'm Francesca Bassi. I'm from ERT SystemX, which you all know. I've been with the ERT since 2 years, almost 2 years now. And before that, I was an assistant professor in an engineering school in the Parisian region, which is called ESME-sur-Rien. So my area of expertise is telecommunications, and now at the Institute, I'm working in the domain of vehicular networks and secure communications between vehicular networks. And today I'm going to talk about another topic, which is radio and computer resource allocation in CRAN. So here you have the overview of my talk. I will start introducing the CRAN concept for those of you who are not familiar with it. Then I will briefly discuss the problem of resource allocation in CRAN in general, and then I will present you some works that we have done on this topic at the Institute. So let's start with the concept of CRAN. So in a traditional mobile network, the radio access is how it is depicted in the picture. So you have devices that connect to base stations, and the base stations connect to the core network through the backhaul. So usually in a traditional setting, you have the base stations that perform radio functions and baseband processing all at the site. With the time, this is something that started to appear in 3G networks and then in 4G networks. We assisted to the separation between the radio frequency functions and the baseband processing functions that now happen in two different places, in two different units that are not co-located. The radio frequency functions stay at the base station, so they form what is called the RRH, the radio head, remote radio head, and the baseband functions happen in another unit, which is called the baseband unit, that can be at some distance from the base station itself, few meters, maybe a kilometer or two. And the two units are connected through an interface, which is called the Common Public Radio Interface. So it's a standardized interface. And over this interface, you have basically the sampled waveform that is communicated to the BBU unit. And the BBU unit is the one doing the digital signal processing. So starting from this new setup, somebody had the idea of, well, taking all the processing that happens in the BBU units for serving several base stations and to place it in the same data center. So this is the Cloudrun or centralized run paradigm that is born. And the idea is to have this data center. It's called a BBU pool that serves many radio heads which are distributed in space, and which communicate through this link with the BBU pool. So this link is called the front haul, and the distance between the base station, the radio head, and the BBU pool now it's several kilometers. Is a big distance. So the idea of making CRAN, of pooling the BBU functions of several radio heads in the same data center has some advantages, of course. It allows for scalability of the system, and it allows to control the cost of deployment and operation of the system we are moving towards mobile networks which are more dense in terms of antennas deployed. So this is a thing that is really important for operators. Then it would allow for to control for the consumption of energy, because it would allow to switch on and off equipments as needed, performing load balancing depending on traffic. And also it would allow to improve user mobility management or intercell interference management, in the sense that these two functions need communication of control information between different antennas. So usually in a traditional system, this is done with control signaling traffic, which is kind of hard to get and to manage. And in the CRAN, we would have the processing of different base stations happening all at the same place. So this information could be shared between the BBU functions of the different radio heads in an easy way. Then we have the challenges. So sharing this information across different BBUs virtualized in the same data center is a problem in itself. So that needs to be solved. Then you have to solve the problem of virtualization in the cloud. And the biggest problem that we have concerning CRAN is that across this front haul, you need to transport a very, very, very high data rate. And the technology to do that, it's not there yet. So a solution to this problem of the bandwidth needed in the front haul is to split the functions that need to be performed in the BBU pool. So maybe you are going to live close to the antenna some of the processing, for example, the modulation. And so instead of having a sampled waveform to travel from one place to the other, you just would have a bit stream, which would consume much less data rate. So today, I'm going to concentrate on the centralized version of CRAN, where all the BBU processing happen in the cloud. But splitting is an active area of research, and it's probably the solution that will make CRAN doable in practice. So I'm moving to the problem of resource allocation in this framework, in this setting. So we have many resources to manage and to allocate, and this is going to happen on different time scales. So first, we have some sort of persistent allocation of resources, which persistent, I mean, this is not something that is going to happen at each time slot, but it's going to last for a period of time. And this is the activation of, or deactivation of subsets of radio heads, and also the clustering of radio heads that get assigned to the same BBU pool. So these are the things you act on when you try to perform energy savings. For example, you deactivate radio heads according to your traffic. And then at each time slot, you need to allocate resources. Some of them are radio resources, so it's the same thing that happens in regular, like in the traditional infrastructure. So you need to perform user scheduling. Who is going to get service right now? You need to assign each device to a radio head. You need to assign bandwidth and time. We are considering OFDMA systems, so you have to assign physical resource blocks to the devices. You need to assign modulation encoding scheme to a modulation encoding scheme to everyone. And this is something that happens in any mobile network. And then in CRAN, you need to assign the compute resources in the BBU pool to each one of the frames that come from or are directed to the RRH. And so in CRAN, with respect to the traditional run, you have that the computer resources are shared. And what changes with respect to standard cloud computing is that computation needs to happen within very hard deadlines because you need to keep the system running in real time. And so usually resource allocation is seen, it is attacked as an optimization problem. And so you can find many angles to define these optimization problems. Sometimes you will want to minimize the power that you use to transmit. So you are going to act on the device RRH assignment and on the power assignment, and you will have constraints that come from the overall power budget and the requirement of service to the users. Sometimes you will want to minimize the energy spent in idle times. And so this is what we were saying just a few minutes ago. You act on which RRH you activate, and on the assignment, on the clustering of the RRH that gets assigned to the same BBU pool. And you're once again working under service quality of service requirement. Sometimes you will want to maximize the throughput that is served by the network, and here you will have to act on scheduling on the radio resource assignment, and you will work under the constraint of the available compute resources that you will have. Anyway, the constraints that are very important in these settings are the capacity of the fronthaul that you should take into account in your problems. The latency constraint on the BBU operations, this is the thing that we were saying before. Processing needs to happen within the hard deadline, and the user quality of service. So this was a very high-level overview of the problem of resource allocation, and now I'm moving to problems that we considered at the Institute, and so I'm going just to give you a little bit of context for this work. There was a project that lasted between 2016 and 2019 at SystemX. This project was called STC and involved SystemX, and then Orange, Nokia, and then Centrale Supélec and Telecom Paris. There was a PhD thesis supervised by Maklouf and co-directed by Maklouf and somebody at Telecom Paris in this project. I arrived at SystemX mid-2019, so I just had the chance to participate in this project during the final leg. And some of the topics that I started to work by that time, I'm exploring them in an internal project, which is called the Explore project, that gives the chance to everyone at SystemX to pursue research topic. And I'm doing this in cooperation with Madi, who is a PhD student at L2S at Centrale Supélec, and Sarah, who is her supervisor, the supervisor of his PhD thesis. So this is a little bit of context. And now we go to the problem that we consider. So as said before, I'm considering a full centralized setup. So everything happens, all the BBU processing happens in the cloud. And so the problem that we are asking, the question that we are asking is the following: what happens if devices try to communicate with the network, and radio resources are assigned as usual. And when these frames hit the cloud and ask for processing, the cloud does not have enough resources to serve the entire demand. What will happen in this case? And of course, what will happen in this case is that somebody will not get service. And the question is, how do I decide who gets service and who does not? So this is the problem. So we are going to consider this problem mainly in the uplink. So I said that there are devices sending data to the cloud. Now here I need to make one of two things more clear. The capacity of the cloud is considered in terms of the processing time that I have available in the cloud within the hard deadline. So when I'm speaking about capacity of the BBU pool, I will speak about time, computation time available in the BBU. And the thing that I will mean by that is computation time before the deadline. So on this plot, to understand a little bit more the problem, you have the processing time that is needed in the cloud to process a radio frame as a function of the MCS of the radio frame. The MCS is the modulation coding scheme. So high MCS mean a high code rate and a high cardinality of the modulation scheme. And here you have three groups of curves that depends on how many physical resource blocks you have to make the transmission of your transmission block. But and then you have in solid line what happens in the uplink, and in dotted line what happens in the downlink. So in both cases, you see that as the MCS goes up, the time you need to process the frame goes up as well. But it goes up more steeply, of course, in the uplink, because when you are transmitting towards the network is the network, so the CRAN who does the decoding, and doing the decoding is more complex than doing the encoding. So this is the reason why we consider this problem, especially in the uplink, because it's more likely that you will have make a provision of resources, and maybe you get extra lucky and everybody gets a good channel and everybody gets a good MCS. And so your resources, computer resources, are not enough to serve everybody. Okay, so I got back to my problem, which was I have a lot of demand, not enough resources. How do I decide which radio frame gets processing? I can frame all of this in the context of an optimization problem. I get an integer linear program. You have it on the slide. I'm not going to go through that. This formulation here allows for two different objective functions. You can switch between one and the other, giving values of 0 and 1 to these two parameters, epsilon and beta. So the first problem corresponding to the first objective function is minimize the number of frames that you lose. So I'm going to assign to serve the maximum number of frames possible. And the second one corresponds to the strategy that maximizes the number of information bits that get processing. So frames are not equal in the sense that a frame with a higher MCS transports more information than a frame with a smaller MCS. So what I'm trying to do here is to give priority to frames transporting a lot of information. And so I can solve this problem in an exact way. Solving this problem is doable, but it's complex as well. And I need to solve it like 1,000 times per second, because this is the duration of the time slot. And so it's not really the best solution to solve it in an exact way, I would be happy if I could have an heuristic to do it at small complexity. So with the exact solution, we are considering 3 heuristics. The first one is round robin. You cyclically allocate resources to each RRH. The other one is short time first. First, you are going to serve frames which have a small time of service. So these are frames that have a small MCS as well. And the third heuristic is high time first. You are going to serve first the frames which have a high computing time, which corresponds to a high MCS, so a high information content. And now we can look at the performance of these strategies. So what we are going to look at is the physical layer throughput as a function of the number of remote radio heads which are connected to the same BBU pool. And we are going to look at the frame loss rate as a function of the number of connected BBU pools. So physical layer throughput. Of course, the exact solution to the ELP problem is the one that maximizes the physical layer throughput. We built the objective function to do that. And we see that the heuristic high time first performs very close to that. So we are happy with these heuristics. And on the other side, we still have an exact solution, which is the blue one that minimizes the number of loss frames in the objective function. So this is the best performing strategy when we look at the frame loss rate. And once again, we have an heuristics, which is the short time first, that performs very close to that. And round robin is in between the two. And now we are somehow happy because we have solved this problem. But we see that what works very good to maximizing the throughput is not well adapted to minimizing the frame loss rate. And so now we are confronted to the question of which one of the two strategies we will take to implement in our system. And at this moment, we cannot answer to this question. And so what we do is, well, take a step back. In this moment, we are allocating resources at the physical layer, and we are evaluating the performance at the physical layer as well. But we are working in a system which has many layers, and at the end of the day, what we care about is the performance up close to the user. So what we are going to do in this case is to move one layer up. So we still allocate these resources at the physical layer where they are, but we are going to evaluate the performance of these strategies at the data link layer, the MAC layer, just one layer on top. And we will see if we can make a decision between these two strategies. So the first thing that we need to say is that when we move one layer up, we have the HARQ protocol that takes place. So the HARQ protocol is very simple. When the device sends a message, sends a frame to the network, to the base station tries to decode. There is a CRC, this is the error detection code, which is attached to the message that allows the receiver to determine whether the information that it decoded is correct or not. If it's not, it can ask for a retransmission. And so there is a finite amount of retransmission that can take place concerning the same message. And so what we want to look at are the performance metrics that we have after this retransmission mechanism has taken place. And so we are going to look at the good put as a function of the number of connected RRH. The good put is the number of correctly decoded information bits after the retransmission process ended. And on the other side, we are going to look at the bit error rate, which is the same principle. We are going to look at the fraction of incorrectly decoded information bits after the retransmission took place. And so if we compare the two strategies that we defined before in this matrix, we see that the strategy maximized the physical layer throughput, gives a better MAC layer good put, and gives us smaller MAC layer bit error rate. So there is no doubt this is the strategy that we are going to prefer to implement in our system. The other thing that we are going to be able to assess now is that this bit error rate that we get with this strategy is still quite high. Normally, bit error rate and good put are conflicting requirements. We cannot optimize both at the same time. And so usually what it is done is we fix a maximum bit error rate that we can tolerate in our system. And within this limit, we maximize the good put. And the bit error rate that we get with this strategy is not within normal quality of service requirements. It's a little bit too high. So the question that we are going to ask is, can we improve on that? And can we improve on that considering the retransmission mechanism, like performing our computer resource allocation, being aware of the fact that it will be a retransmission mechanism on the top. And this idea comes from a very simple observation. Imagine that the last retransmission of a message gets lost. So it gets lost because it doesn't get processing in the cloud. So what you are going to waste is all the resources that you spent for this present transmission, but also all the resources that you spent for the previous transmissions. So it's extremely inefficient to drop the last HARQ transmission of a message. So based on that, we do what we did before. We conceive an optimization problem. Is still an integer linear programming optimization problem. We use the same framework as before. We are going to consider different objective functions corresponding to different strategies, and we are going to toggle between one and the other by setting the values to these parameters. Now we have 3 parameters. So we are going to keep the 2 strategies as before. We are going to add a third, which is I'm going to get priority to those messages which are old in HARQ, in the HARQ process. The last retransmission, the one before the last retransmissions, they will get processed. And then the last one is a combination of the maximized phi throughput and maximize the HARQ age of the processed frames. So you will get an objective function, which is the sum of these 2 terms. So we are going to see how they perform. So starting from the good put, maximize phi throughput stays the better choice if the good put is what you care about. It's the only thing you care about. And the other 2 strategies are well, improving a little bit with respect to minimize the number of lost frames, but not so much. But on the other hand, if you look at the bit error rate, you see that you have a huge improvement in considering the hierarchy retransmission age and in combining retransmission age with high throughput maximization, you have an even bigger gain. So we had a good idea after all. And now, okay, as before, this is still an optimization problem. It takes forever to compute. It's not a good idea to use it with this frequency. So we need to think about alternatives that we could use with small complexity. And so the idea here is to use a probabilistic algorithm to assign frames to the available computer resources. So the algorithm is very simple. You have your demand. You start sampling the frames that require processing one by one. And for each frame has a probability phi I, which depends on its retransmission age and depends on the information content of the frame. And so this frame gets assigned resources in the BBU pool with this probability. So you iterate this procedure on your demand until all your processing resources are saturated. And so you get your resource allocation. And by toggling these three parameters, you can switch between the four considered strategies as before. And so you get, on this plot, you get the results that you have with the probabilistic algorithms in dotted lines and the same color that you have for the exact solution. So you see that you are going to lose quite a bit in the performance when you consider the beta rate, when you use the probabilistic algorithm with, if you compare to the exact solution. And this translates in a slight gain in output, which is expected. And that's it. If you can solve your problem exactly, you are going to have a better performance. But there is another thing we can do with the probabilistic algorithm that we couldn't do for complexity reasons with the exact algorithm, which is explore all possible mixing of these four strategies. So far, we have toggled these parameters 0 or 1, just to select the strategy and incorporate it in the objective function. Now that we have an algorithm with a very good complexity, we can numerically explore mixed strategies that would come by giving the ability to these parameters to take real values between 0 and 1. And we can explore the entire realm of possibilities, because we can basically make this parameter vary and check the performance that we have. And this is useful because what we want is to understand if there is a combination of these that gives us the best possible trade-off between the beta rate and the output. And so this is what we have done. And you see the representation here in this plot. So we have plotted the output against the beta rate for a fixed number of RRH connected to the same BBU pool for various value of epsilon, alpha, and beta corresponding to various mixing of these strategies. And then here in color, yellow, blue, violet, and red, you find the strategies, the pure strategies that we discussed so far. And then the last thing that you need to know is that a good trade-off between good put and bit error rate is high good put, so you move to the right, and of course a small bit error rate, so the best performing strategies are in this quadrant here. And so you see that we had the chance of selecting the best possible strategies among the considered one in the first place, because trying to maximize the phi throughput, also taking into account the retransmission age of the frames, gives you the best trade-off that we could find in this study. So now what we would like to do is to extend this work. So the idea is to try to perform using scheduling and joint radio and compute resource allocation. So we would like to have a framework that can describe the overall problem to perform this resource allocation all at once. Of course, there are problems in doing so, mainly because not all these decisions need to happen at the same time scale. And so we have identified Markovian structures as the more adapted to describe the problem, and then Markov decision processes would be the tool that we would like to use to solve this resource allocation, global resource allocation problem. And so far, we are working in a system level simulator, because we need, well, first we need to have a representation of what happens at phi at Mach, which is small enough and that we can use in simulation to test our strategies. And then we need to use this to model the transition matrix in our Markovian process. So this is what we are working on now with Madi and Zahar. And it's not done yet, so maybe we will have the chance to discuss it another time in the future. And so if you have questions.
Thank you, Francesca. So, question in the audience?
Well, perhaps, I mean, I'm not an expert at all, and I'm not sure my question makes, full sense. But I mean, you discuss these hard deadlines, right? So there is a whole branch of computer science which goes about, satisfying real-time constraint in, say, on various types of wireline networks, right? You have. And so, here, you still have lots of randomness, right? So you cannot guarantee any real-time, hard constraint in this framework. You try just to, if I get it correctly, to minimize the number of packets missing the whatever hard deadline. This is your aim, right? So is my understanding okay?
Yeah. If a packet doesn't get processing within the hard deadline, is as good as lost.
It's
because
lost, right? Okay.
Yeah, it's lost. So we drop it. Yeah.
Okay. Thank you. Yes. Right. So, and when very often what you hear when you listen to talks on 5G is that you get this very small time, say 1 millisecond, but these are just again statistical guarantees with no hard deadline, right? So and what you do here is try to minimize perhaps the number of packets lost, but this is in no sense a deterministic guarantee that packets of a certain class will be transmitted with no loss.
Yeah. let me see if I interpret correctly what you are saying. So usually you have concerns about the latency of information traveling in the network. This is what you talk about when you speak about URL and this quality of service.
Exactly.
Something that is not the same thing as this hard processing deadline. This hard processing deadline here comes basically from the HARQ process. So if your destination doesn't hear about you within a deadline, it will consider the packet lost. Okay, so you need to have enough time to decode the packet and send back your acknowledgement or your retransmission request. So this is a deadline that comes in number of time slots, and a time slot can be smaller than what the duration we have considered, but it will still be the same number of time slots. So they are two different deadlines. I'm not sure if I could explain correctly. What I meant to say is that in the moment when you are going to consider a system that can work with a smaller latency, you would still have a fixed number of time slots, this same fixed number of time slots to consider.
Mm-hmm. Okay, thank you.
Other questions?
Francesca,
yes.
if I may, Fabio Pianese. I worked on this problem in the past, and I was wondering, how do you handle, or if you are interested in fairness across the users, and whether this is part of the kind of follow-up work?
This is where I would like to go. Yeah, the plan is to consider user scheduling with of course, a fairness or some sort of quality of service requirement on the part of the users. Because yes, I find that what we can do now, how we can approach this problem now is not enough to reply to this question and to answer this question. And yeah, I find it very interesting. So you are actively working on this?
Not really. It was like 10 years ago. It's been a while. But yeah, I mean, perhaps I switch to my headphones since noise coming out of the phone.
So, Fabio?
Yeah, I have got problems with my setup at home.
Yeah.
The fairness basically is a problem that appears because whenever you are applying some sort of scheduling decisions at a lower level, such as you're doing with a sort of physical layer data, I mean, there is going to be a consequence. For instance, if you basically maximize the rate for the best users, then basically you're shuttering the door to anyone else who has got. So I really think to kind of make justice to this work, there should be also an evaluation of the fairness at the moment, and not only as a part of future work. And then I have a more basic question, because of course we started thinking about this kind of setup back in 2010 when the Chinese came up with, let's say, let's do CRAN, and it was, we saw it happen live. And but first, where is your scarcity coming from? In a sense, the point of putting things in the cloud was that CPUs are cheap. We will have enough cores for everyone. So perhaps there's going to be other sources of scarcity, but CPUs is that one?
Yeah, the idea is that if you want to make energy economy, you should be managing the active CPU power in your BBU pool as well. And so the idea is that you are able to make some sort of provisioning. So you have two ways of doing that. Well, you can over provision, so you will be safe in any case. Or you can try to you can try to allocate as many resources as you think you will need. And then we saw that what happens is that how many resources you will need will depend, well, heavily on your MCS, which depends heavily on the instantaneous quality of your channel. And so we imagined that this problem might happen in reality. Then, of course, if you go to an operator and you ask them, how are you deploying your CRAN? I think at this moment they are deploying like with an allowance for CPU processing in their system. But still, this is this problem here is in line with the idea of optimizing the resource expenditure, like the energy expenditure of your system. So this is how we started to look at it in the first place.
Thank you.
Other questions? On my side, I also added the question about fairness, but so you answered already that. I have another question about your slide 28.
Oh, yes.
Yeah, so I really like the idea of looking by varying the different parameters, what is the best according to bit error rate and good put. But I noticed that the good put is not varying a lot, in fact.
Yeah, it's not
less than 1% or 2%.
Yeah.
So is it really useful then to, what is the usefulness in such a case of trying to optimize the good put if it doesn't vary so much? In particular, when we consider that maybe other points that are not considered here, like fairness, for example.
Yeah, sorry, I think that the problem is that I really made a bad choice on the x-axis when I extracted that plot, because I probably selected something which is here in the middle, and the good put between the various strategies doesn't differ that much.
Okay. Yeah.
So if you increase the number of the RH, you see that the difference.
It varies, but not so much. But it varies more.
It varies, but
a bit more, but not so much.
No.
Not a so big difference. But yeah.
No. The main focus, I mean, the biggest difference you have it between the two original strategies that we considered at the beginning. And the whole point in adding HARQ is like to take the bit error rate down. So
that is, I understood that well, and we see on the slide 28 that for the bit error rate there is a large difference. But
yeah, the bit error rate really is heavily affected by this, taking into account the HARQ. So yeah, in the exact solution, you can see a difference between these two strategies. Here, using the probabilistic heuristic, this difference disappears, but still you can see that taking this into account is really beneficial for the probability of error, for the bit error rate, sorry.
Yeah. Okay, other questions?
I would have a one.
Yeah.
Hi, Francesca. Thank you for the talk. It's a very important topic in my point of view, because from operators, the cost of backhaul and fronthaul is extremely important when designing and planifying such a network. And as you know, in the 5G environment, the concept of a middle haul has been introduced, which enables to split the BBU by introducing not just a link, but a network in between. And my question is, from your point of view, when moving into such an architecture, how your results will be impacted?
This is a very good question, and I didn't have the chance to think it through. These results depend on depends on this evaluation here, which is how much processing time you need to do the BBU processing. And of course, if you split the BBU, this profile here will not be the same. So the first thing to do in my point of view would be to go and try and see if this problem would arise in that situation or not. And I don't have an answer right now.
Okay. And my second question is about the fact that, as you know, with the mobile edge computing together with the BBUs, we could have other type of functionality which are more related to the applications themselves, with an understanding of what the traffic you are conveying is. And I was thinking about how do you see the possibility of a kind of a joint optimization, meaning making the optimization you are doing, but by taking into account the requirements of the different flows you are transmitting.
Well, requirements of different flows in terms of different quality of service. This is something I would like to do, and which is planned. And so the idea is to formalize these different requirements. This radio bearer here has a function, and this other has another, so they have different requirements. And if it is what you mean, yes, I hope I will have results on that later on to discuss with you.
What I was thinking about is a step forward, is to say that among the things that you could do in this location where you're putting the BBU intelligence is, for example, to be able to store some flows that have no delay constraints when you have not enough resources and you want to give priority to other flows. So the fact that you have a storage and computing resources at this level for the, for the application level may help you to do the optimization you are describing here, right?
Yeah, but the problem is that if I understand correctly, like computing for the application has a lives in a time which is not the slotted time of transmission. So it's the latency we were speaking about with Francois before. You want to minimize that, but it's not the same time grid. So this time grid here that we are considering, this time slot here, is the time slot that comes from OFDMA, like from the fact that you need to start transmitting frames within a certain rhythm. And so I'm not sure that the interaction between the two would be so straightforward. Okay. I mean, the thing of giving priorities, quality of service and priorities to different radio bearers, yes, definitely yes. This has an impact on application, but the rest, I don't know. Maybe I need to like think it through. I don't see the immediate connection now.
Okay, thank you very much.
Thanks to you.
Other questions? Okay, so thanks again, Francesca, for your talk.
Thank you.
Thank you very much.
Thank you.